So last day, I talked about the assumptions and I sent you the materials and you have the books with you. So I think more or less you framed some idea about the assumptions we need to consider to develop the classical linear regression model. Now, some students may have some difficulties regarding the notion of degrees of freedom. In due course, I'll discuss the matter of degrees of freedom once again. So today, I'd like to move towards estimation procedure. Okay, so you have idea about the structure of a regression model. So you have n number of equations here and k number of parameters we need to estimate. Actually, we have intercept term in the model and we have k minus 1 number of regression coefficients. All these regression coefficients are appearing with the explanatory variables. These explanatory variables will also work as control variables in our analysis. Okay, so this is the structure. Given this kind of structure, we are understanding that to move further, we need to estimate the parameters of the model. Now, if I consider a very simple case, suppose the demand equation, okay, the equation with which we start reading the subject economics. So the demand equation is given by, say, yi is equal to beta naught plus beta 1 x1i plus ui. As long as we cannot estimate beta naught and beta 1, we cannot argue whether x1i will be able to explain the variation in yi. If I consider yi to be the quantity demanded and xi to be the price of the commodity, as long as we cannot estimate the parameter beta, we will be not able to move towards the conclusion, whether xi, that is the price, can explain yi or not. Only estimation, even estimation will not work. After estimation, we have to go for hypothesis testing. And when we will reach at hypothesis testing, and if we find xi to be significant, or the coefficient to be statistically significant, then only we will be able to argue, yes, really price can explain the variation in quantity demanded. And the sign is also important, whether this beta is positive, beta is negative. Looking at the sign, we will understand whether xi and yi is positively related, negatively related, etc. Now, in a regression model, when we are considering 10, 12 explanatory variables, each of the coefficient is important to be. Okay, so we need to complete the process of estimation. We need to look at the signs, whether we are getting expected signs or not. If not, what can be the logical reason for getting this kind of different sign, which is contradicting the theory? And after completing estimation, we will be able to move towards hypothesis testing, and we will get a complete picture whether these x can explain y, these set of x cannot explain y, etc. So we are understanding, once we consider the assumptions and prepare the background, then we have to move towards the estimation process. Now, in a regression model, if we consider a k-variable regression, the structure is given by y is equal to x beta plus u, where x is a matrix, y, beta, u, these are the vectors of different orders. Now, if u is the random error or the series of random errors, in that case, our natural instinct is telling us we have to minimize these errors. If I can minimize this error, my estimated model will be very, very close to the theoretical model or the mathematical model. Okay, so my estimation will be very close to that of the true model. Now, in the process, we will find that this ui is function of beta 1, beta 2 up to beta k. And since it is a function of all unknown parameters, this u cannot be realized. We cannot realize the random error. So what we do, we consider the estimated value of this error, which we call residual, which we generally define by small e. So from error, we will move towards residual, where residual will be function of beta 1 hat, beta 2 hat, up to beta k hat. So while u is function of all unknown parameters beta 1 to beta k, and therefore unobserved, e will not be unobserved. We will be able to realize the residual.
Ma'am, we can't see the
Ma'am,
I'm
could you show us the slide?
I'm not showing anything. I'm telling you the story. I'm not showing you anything.
Okay,
Okay,
ma'am.
ma'am. Sorry, ma'am. We thought that we couldn't.
Okay. So you did all these things in your earlier semester, I hope. Only I'll extend this thing only for the k variable framework, isn't it? You know all these things, isn't it? You cannot be realized, etc. You need know all this thing. Nazma,
Yes, ma'am.
you know all these things, isn't it?
Yes, ma'am. Notions, the three variable models, that one.
No, that you cannot realize the random error u. Therefore, we bring the idea of residuals, etc.
No, ma'am. That part we hadn't.
So why you considered the minimization of residual sum of squares then? I hope you did all these things. Okay,
No, ma'am. Residue. Okay.
okay. Everybody did all these things. Okay, everybody. Those who had econometrics for 2 variable courses, all Calcutta University, Jadavpur University, St. Xavier's, Presidency, Vadwan, Vidyasagar, everywhere. This course is there, and you went through this kind of syllabus. Okay. However, no problem. Therefore, I'm trying to tell you the old story. Actually, we are revising the old story only, and that I'm giving a new package because it's a k variable analysis. That's all. Okay, so let me show you the slides. So whatever I told you, if y is proposed value, last day I talked about the proposed value. Y is the value where there is no error at all. Okay. So y is the value where we are considering y is equal to beta 1 plus beta 2 x2 1 suppose x2i plus beta 3 x3i plus up to beta k xki. There will be no error at all. It is the fixed model which we are getting from the economic theory, like q is equal to a minus bp, or q is equal to a plus bp. This kind of model, there is no error in it. So if y is the proposed value and yi is the observed value, then ui is nothing but the difference between the observed and the exact. Y is the exact functional form, okay, and yi is the observed value. Ui is the difference between observed and exact. So yi is the observed, and minus y, which is a function of beta 1, beta 2 up to beta k. Since beta 1, beta 2 up to beta k are unknown, y as a function of beta 1, beta 2 to beta k, this is also unknown, and hence ui is not realized. We estimate the unknown regression coefficients beta 1, beta 2 to beta k, and derive the estimated value, which is given by yi hat is equal to beta 1 hat plus beta 2 hat x2i plus up to plus beta k hat xki. So what I am telling that UI, which is based on unknown population parameters, beta 1, beta 2 to beta k, cannot be realized. This cannot be realized. Okay. So we estimate the unknown regression coefficients and can generate yi hat. And the difference between yi and yi hat, that is the observed and estimated, can be realized, and this is called nothing but the residual. So from UI, we are moving towards EI, which is the difference between the observed and estimated value. So we started with differences between observed and actual. We understand that this UI is not realized because Y is a function of unknown parameters, and therefore UI is also a function of beta 1, beta 2 to beta k. So what we need to do, we need to frame a function of estimated values of the parameters, and the function of estimated values of the parameters is given by yi hat, difference between observed and estimated. Okay, that is also an unexplained part, and we cannot call this error, rather we call this residual. Okay, residual. Now this residual is a function of beta 1 hat, beta 2 hat up to beta k hat. That is, it is a function of estimated values of the parameters, and therefore it is observable. While UI is not realized, not observable, EI, residual, that is observable. We can realize the values of the residuals. Now these residuals are some kind of estimators of UIs. Look at this note, EI is not a regular type estimator because UI is a variable. Generally, we find out estimator for unknown parameters. Here, what we are doing, UI is a random variable. However, it is not realized. Therefore, we are trying to estimate it. Since we generally estimate the parameters, not the variables, therefore, we are telling that this EI or the residual is not a regular type of estimator. However, we understand we can use this notion of EI or residual in our further analysis of estimation, hypothesis testing, etc. Now, if EI is the residual, which we can realize, our objective will be to minimize this residual. Okay, so let's move to the board. Okay, so for the time being, just ignore the things we have in the board. Rather, let's look at this part. So UI, the problem with UI is not realized. So we are bringing EI here, the notion of residual, which is a kind of estimator of EI. So in the regression analysis, while we will go for estimation, our objective will be minimization of EIs. So we will like to, our objective will be minimization of EI. However, this EI can be positive, negative, etc. This residual can be positive, this residual can be negative. To avoid the directions of EI or directional claims regarding residual, we consider EI square, you know. This EY square will be free of any sign or any direction, okay? So we can minimize EI square rather than EI if we need to avoid any kind of sign here. Second, we will not minimize E1 square, then E2 square, then E3 square, etc. So sequentially, we will not minimize EI square. Rather, simultaneously, we will try to minimize the entire error possibility. Therefore, we consider this is called so in the due course, while we will try to find out the estimated values of the regression parameters, we will minimize this summation EI square, which is called residual sum of squares. In a two variable case, we minimized sorry. Okay, so we considered del RSS by del alpha hat, and using the first order condition of minimization, we set this to be equal to 0, and we get the normal equations. Solving these normal equations, we get the values for two unknowns. Okay, can you remember this concept? Can you remember this concept?
Yes, ma'am.
So here we will do the same thing. Everything we need to present in terms of matrix algebra because we are considering all k variables. Okay, and instead of two normal equations, we will have a set of normal equations because here we are dealing with k number of parameters. So the similar thing I have to do for all k parameters. So del RSS by del beta 1 hat del RSS by del beta 2 hat, and this thing will be extended up to del RSS by del beta k hat, and we will generate k number of normal equations, and solving these equations simultaneously, we will get the estimated values of the parameters. So this I am trying to tell you. So from error, first we define error, which is the difference between the observed value and the exact value. Now, there is some problem in realization of this error as it is a function of unknown parameters. Therefore, we move towards the notion of residual. Residual is yi minus yi hat. So, this ui is this, whereas this ei, the residual, is this is the difference between the two. And as we incorporate this difference, EI becomes functions of all estimated parameters, and therefore we can realize it. We can work with this. Okay, so now it is reasonable to require that beta 1 hat, beta 2 hat to beta k hat should be such that these errors of estimate are as small as possible. However, it will not enough to minimize the sum of these errors, which may be positive or negative, may even add up to zero for a line for which individual errors are of high magnitude. In most cases, a satisfactory method of determining beta 1, beta 2 to beta k would be the method of least squares, which consists of minimizing the sum of squares of the errors of estimation. So I hope you understood the mechanism. So next we move towards OLS estimation. We minimize the residual sum of squares with respect to beta 1 hat, beta 2 hat up to beta k hat, the estimated values of beta 1, beta 2 up to beta k. Now here we define RSS residual sum of squares by the term E prime E, E prime E. Now we know by definition RSS is summation EI square. So we need to understand, E prime E is equivalent to summation EI square or not. So let's take this once again. Okay. So what is this E vector? Anyone, please tell me what is this E vector, the residual vector. What will be the order of this vector? It will be equivalent to U. So what will be the order of this vector? Residual
Y
is
minus
equal
X
to
beta
U.
hat.
What will be the order? I want to know the order.
I mean, n cross 1.
N cross 1, yes. So sorry. So it will be like this, okay? So it is, the okay, so if I consider E prime, so this will be a row vector. What will be the order? What is the order of this E prime?
1 cross n.
So if I consider E prime E, what basically we are doing, we are multiplying the row vector with the column vector. Everybody? And as we are doing so, what we are doing, we will move to this direction and is this equivalent to summation EI square or not? Everyone?
Yes, ma'am.
Okay, so we are getting E1 square plus E2 square up to En square, so which is equivalent to summation EI square. So what we are finding that E transpose E is equivalent to summation EI square. Okay, so what we did in case of two variable in terms of summation EI square, here we will do the same exercise considering E transpose E, because E transpose E is the residual sum of squares. It is nothing but residual sum of squares. Now tell me, E transpose E is a scalar or a vector or a matrix? E transpose E. Is it a scalar? Is it a vector? Is it a matrix? Anyone, please? What is the order of E transpose E?
And 1 cross 1.
1 cross 1. So if the order is 1 cross 1, is it a vector, is it a scalar, or is it a matrix?
It's a scalar.
So it's a scalar. Okay, so it's a single term basically. It's a scalar. This is a single term. It's a scalar. So we minimize this RSS with respect to beta 1 hat, beta 2 hat to beta k hat to get the estimated values of the unknown parameters. RSS is E prime E, which is equivalent to summation EI square and a scalar. So I hope you understood these terms. So next, I'm coming to the expression of E transpose E in terms of the parameters of the model, because I need to consider the minimization of this E prime E with respect to parameters of the model. So I need to apply calculus on it. And therefore, I need to bring the term beta hat here. Now, from our previous notion, we got the idea E is nothing but y minus x beta hat. E is y minus y hat, and y hat is x beta hat. So E is y minus x beta hat. So it is y minus x beta hat transpose y minus x beta hat. So if I multiply the thing, so if I apply transpose on the first part, it will be y transpose minus beta hat transpose x transpose. So if I multiply y transpose by y, so the first term is y transpose y, then I am multiplying this y transpose with the second term in the second expression, x beta hat. So it is y transpose x beta hat, then minus, I'm multiplying this y with the second term, which is beta hat transpose x transpose. So beta hat transpose x transpose y plus beta hat transpose x beta hat transpose x beta hat. So multiplying E transpose with E, we are getting all these four terms, y transpose y minus y transpose x beta hat minus beta hat transpose x transpose y plus beta hat transpose x beta hat. So please tell me whether the second line is fine with all of you. Is it okay? So if this is fine, next, y transpose y I'm keeping as it is. Instead of y prime x beta hat and beta hat prime x prime y, I am writing minus 2 y prime x beta hat. That is twice of this term, Okay. Now, I hope you have pen and paper with you. If you consider the transpose of the third term, transpose of beta hat transpose x transpose y. Take transpose of beta hat transpose x transpose y and tell me what you are getting. Take transpose of beta hat transpose x transpose y and tell me what value you are getting.
Beta hat x y transpose.
Would you please once again? Transpose of beta hat prime x prime y, what you are getting. If we take transpose of this second term, beta hat transpose x transpose y. Yes, Nazma, would you please repeat once again?
Yes, ma'am. Beta hat x y transpose.
Beta
Same
hat,
as the previous.
beta hat x y transpose. The ordering is not right. Rudra?
Ma'am, Y transpose X beta hat.
Y transpose X beta hat. Yes, that is the right answer. Now, so when you are taking transpose of this thing, the order will change, isn't it? Here, when we considered transpose of X beta hat, we got beta hat transpose X transpose. So, following the same thing, when you will take transpose of this entire thing, it will be no more beta hat X Y transpose. Rather, it will be Y transpose X beta hat, so the order will change. So exactly what we will get, that is like this. Transpose of the third term is similar to that of the second term. And if we look at the order of each and every term. Let's look at the order of each and every term. Now, what is the order of Y transpose Y? What is the order of Y transpose Y? Be first. What is the order? Yes, Shairi Bhattacharya. Shairi, what is the order of Y transpose Y?
N cross 1.
N cross 1? Anyone else? Is it N cross 1?
Ma'am, 1 cross
1
1.
cross 1.
1 cross 1.
Cross 1.
1 cross 1. Okay, because Y is of order N by 1, Y transpose is of order 1 by N. So Y transpose Y is nothing but 1 upon N into N by 1. Okay, so it is 1 by 1. So first term is a scalar where the order is 1. What about the second term, Y prime X beta hat? What is order of Y transpose? 1 by N. What is order of X? Anyone? Anyone, please.
N cross K.
N cross K. So the first term is 1 by N, then N by K. And what about beta hat?
K cross 1.
So what is the order of the entire term?
Ma'am, 1 cross 1.
1 cross 1. Very good. And what about the second term? Beta hat prime, what is the order? Beta hat is of 1. So what is the order of beta hat prime?
1 cross K.
1 cross K, then K cross N, then N cross 1. Again, it is of order 1 upon 1. So all the terms here, the first term, second term, fourth term, for every term you consider the orders. You will find all are scalar. E prime E is a scalar, so all the right-hand side terms are scalar. So if Y prime X beta hat and beta hat prime X prime Y, these are scalars, this means these are single numerical figure, say 5. This is -5, this is also -5. So we can easily write the term as -10. Okay, so I'm following the same logic here. I'm considering the two terms as identical two scalars. So I am writing or presenting these two terms as a single term minus 2 Y prime X beta hat. And keeping this beta hat transpose X prime X beta hat like this. So these two second and the third terms will get the same value. So I'm combining these two. So since both Y prime X beta hat and beta hat prime X prime Y are scalars, and one is the transpose of other, hence both are equal. Transpose of 5, say 5, if it is a scalar, a single number, transpose of this value will be the same value. Okay, so Y prime X beta hat is a linear function of beta hat, and beta hat X prime X beta hat, this is a quadratic function of beta hat. So the second thing apart from the fact that we can present E prime E with the help of these three scalars, the other finding or other observation, if I look at E prime E is a function of linear function of beta hat. If I consider the second term, so y prime x beta hat is a linear function of beta hat. And if you look at the third term, it is a quadratic function of beta hat. This is a linear function and second one is a quadratic function of beta hat. Now, why I'm mentioning all these observations? Because in the next step, I'm going to take derivative of E prime E with respect to the parameters of the model. So if I have linear function, in that case, differential calculus will give me one particular rule by which we will be able to derive the normal equations. If I have the quadratic expression, in that case, our differential calculus will define the other rule by which I'll be able to find out the normal equations. So now we will move towards estimation, where we will take derivative of this E prime E with respect to all beta hat values. That is starting from beta 1 hat to beta k hat. All these values I need to consider, all these derivatives I need to consider. While I am taking the derivatives, please remember these things. There are beta hat in two terms only. The first term will never appear because it does not consist of any beta hat. However, our work will be concentrated on the second and the third term. Second term is a linear function of beta hat, while the third term is a quadratic function of beta hat. So next, we are going for linear and quadratic forms, we are going for matrix differentiation. So you may not be familiar with matrix differentiation that much, therefore follow the note and then I'll come back to this particular this particular equation where we have to apply this kind of differentiation. The first, differentiation of linear form. So I'm considering any linear form given by, say, summation ci xi. I is running from 1 to n. So summation ci xi, that indicates c1 x1 plus c2 x2 plus up to cn xn. So I hope you are understanding this is a linear construct. In terms of matrix algebra, we can present this, that is c1 x1 plus c2 x2 plus cn xn, this in terms of C transpose X, where X is of order n by 1 and C is of order n by 1. Okay, so both C and X we are considering are of order n by 1. So if I consider C is of order n by 1, that is there are n number of rows and one column. So it's a column vector like this, C1, C2 to Cn. This is a column vector, okay? So when I'm considering C prime, I'm getting a row vector, C1, C2 up to Cn. Now X is a column vector, n by 1. So I am multiplying a row vector C prime with a column vector of order n by 1. So I hope you are understanding. I am getting C1 x1 plus C2 x2 up to Cn xn, which is equivalent to summation Ci xi. Any question, any doubt about how we can write summation Ci xi as C prime x when C and x are both of order n by 1?
Ma'am, can you explain this again?
Which one? The multiplication or anything else?
How summation Ci xi became C prime x?
Okay, so C is basically is of order n by 1. So if I consider C prime, we are getting this kind of vector. Okay, x is also of order n by 1. So C prime x will be multiplied with the rule is like this. So as you multiply, okay,
Yes, ma'am, got it.
so summation Ci xi is equivalent to C prime x. So, and C prime x is a scalar. It is C1 x1 plus C2 x2, etc. In terms of the matrix algebra, if you try to understand, C prime is of order 1 upon n, x is of order n by 1. So C prime x is of order 1 upon n, 1 by n. So it is a scalar. So if I take derivative of C prime x with respect to x, basically what I have to do, x is a column vector. So column wise, I can take derivative with respect to x1, x2 up to xn. So I'm taking derivative of entire sum, del of summation Ci xi or del of C prime x with respect to x1, then del of summation Ci xi or C prime x with respect to x2, del of C prime x with respect to del xn. So with respect to all the values in the parameter, all the values in, in x, we are taking the derivatives of C prime x. Now, as I am taking derivative of C prime x with respect to x1, actually I am taking derivative of C1 x1 plus C2 x2 plus up to Cn xn with respect to x1. If I take derivative in this way, I'll get back C1. Next, if I take derivative of C1 x1 plus C2 x2 up to Cn xn with respect to x2, I'll get C2. Finally, if I take derivative of the same expression with respect to xn, I'll get Cn. Okay, so, I have C1 x1 plus C2 x2 plus Cn xn. One by one, I am taking derivative with respect to x1, then with respect to x2, then with respect to xn. So vector wise, I'll get back C1, C2 up to Cn. So that I have here. So I'm getting back the entire C vector. So I'm starting with differentiation of C prime x with respect to x, and I'm getting back C, not C prime. I'm getting back C. Now coming back to our analysis, I have the term minus 2, I'm just not considering at this moment. I have the term y prime x beta hat, and I have to take derivative with respect to these beta hat vector. I have to take derivative of this term with respect to beta hat vector. Okay, so if I take derivative with respect to beta hat vector, the value I'll get, that will be x prime y. Okay, the standard thing is I'll get minus 2 y prime x. However, it will not happen here. The position of the transpose will change. So if I take derivative with respect to beta hat, the term y prime x beta hat with respect to beta hat, I'll get x prime y. Okay, so if I take derivative of y prime x beta hat with respect to beta hat, I'll get x prime y. I started with C prime x. After taking the derivative, I get C. So when I am taking derivative of y prime x beta hat, following the same logic, I'll get back the transpose of y prime x, which is given by x prime y. So if I take derivative with respect to beta hat, my term will be minus 2x prime y. Next, we are moving towards differentiation of quadratic form. So here also, I'm considering an example. Consider the form x prime ax. X is a vector of order n by 1 as I considered. Capital A is a square symmetric matrix of order n by n. It is a squared symmetric matrix of order n by n. So if it is a squared symmetric matrix, A is equivalent to A transpose. To simplify the entire context, I am considering n to be equal to 2. So I'm considering a matrix of order 2 by 2 and X is a vector of order 2 by 1. So for n is equal to 2, the expression can be presented as x prime ax is equal to x1, x2, then the matrix a11, a12, a12, a22. We can write this a12 or a21 since it's a symmetric matrix. I'm keeping it a12. Actually, a21 is similar to that of a12 and multiplying it by x1, x2. So as I do so, if I follow the steps one by one, first I'll follow the multiplication in this format, row column in this format. So I'll get a11, x1 in this format. I'll get the terms, So first I'll multiply x1, x2 with this, and then I'll again multiply the entire thing with x1, x2. So if you do all these things, I'll get finally a11 x1 square plus 2a12 x1 x2 plus a22 x2 square. Okay, so first you multiply this with the matrix and you will get one matrix. Then you multiply the terms with this column, the last column. You will get the values a11 x1 square plus 2a12 x1 x2 plus a22 x2 square. So whatever important, here we have the square terms, square terms. So if I take the derivative del x prime ax by del x, basically I have to take derivative of del x prime ax first with respect to x1 and then with respect to x2. If I take the derivative with respect to x1, from this equation I am getting 2a11 x1 plus 2a12 x2. Okay. From the second expression, I'm getting 2a12 x1 plus 2a22 x2. This is equivalent to 2ax. So I can take 2 common, so you will get 2, and then you are getting a11, a12, a12, a22, that is the A matrix that has been multiplied with x1, x2. So if you actually multiply these row vector with this matrix, you will get these terms, okay? And then you are post multiplying it by another x1, x2, so you are getting the square and the cross products. Now, if you take the derivatives, you will get this kind of expression, 2a11 x1 plus 2a12 x2, 2a12 x1 plus 2a22 x2, which is equivalent to 2ax, which is equivalent to 2ax. So coming back to our third term, which is beta hat transpose x prime x beta hat. This x prime x is equivalent to our A matrix. Now, if you look at x prime is of order k by n, and x is of order n by k. So x prime x is of order k by k, which is a square symmetric matrix. Okay, and this is post multiplied with beta hat prime, pre-multiplied with beta hat prime and post multiplied with beta hat, like the earlier case. So here I'm considering the similar kind of context, pre-multiplying the symmetric square matrix with x prime and post-multiplying it by x. So here also the same thing, pre-multiplying it by beta hat prime, post-multiplying it by beta hat. Now, if I take derivative with respect to beta hat, actually I'm taking derivative with respect to beta 1 hat, beta 2 hat up to beta k hat. The final result I'll get will be given by 2, the matrix A, here x prime x, into beta hat. 2ax, that was the result, okay? I started with x prime ax, took derivative with respect to x. I got 2ax. So here, following the same logic, I'll get 2x prime x beta hat. Any question, any problem regarding the derivative part? Once you understand these parts, I'll plug these values. The first thing I got, that is x prime y, and the second thing I'm getting, this I'll plug in the del RSS by del beta hat equation. And then I'll get a set of normal equations. So first tell me whether anyone has any problem regarding the derivative, etc. Is it fine to all of you?
Yes, ma'am.
Shreya, would you like to tell me anything? Shreya Noshkar? Anyone has any problem? Twinkle, you are understanding all the matters?
Yes, ma'am.
Okay, fine. Upali?
Yes, ma'am.
Okay, very good. So if you understand all the derivatives, etc., in the next step, I'm considering del RSS by del beta hat. Mark that it is the set of k number of equations. This is basically del RSS by del beta 1 hat, del RSS by del beta 2 hat, up to del RSS by del beta k hat. So this is a set of k number of equations. So this k number of equations can be presented as minus 2x prime y plus 2x prime x beta hat. And by the rule of minimization, I can set this first order condition to be equal to 0. Minus 2x prime y plus 2x prime x beta hat is equal to 0. So if I do so, basically I'm getting this set of k number of equations, x prime x beta hat is equal to x prime y. This is the set of k number of normal equations. So in case of two variable analysis, I get two normal equations. In case of k variable analysis, we are getting k number of equations. We are getting k number of equations, okay? K number of normal equations. Now, if I solve this equation simultaneously, we derive all values of beta hat. Actually, we will be able to derive beta hat vector, okay, all beta hat values, beta 1 hat up to beta hat k, and this is given by x prime x inverse x prime y. If I want to solve for beta hat, the beta hat values will be given by x prime x inverse x prime y. If I want to bring this x prime x to the right hand side, it is basically x prime x inverse. So the value of beta hat vector, beta hat OLS vector, is given by x prime x inverse x prime y. X prime x is a k by k square symmetric matrix, and rank of x prime x is minimum of rank of x or rank of x prime, which is k, because it is a k by k square matrix. So rank of x prime x is equal to k implies x prime x is not a singular matrix. So determinant of x prime x exists, and therefore x prime x inverse exists. So logically, if we can ensure, we will be able to calculate x prime x inverse, beta hat OLS, beta hat vector OLS can be presented by a series of values given by x prime x inverse x prime y. Now, if you look at this estimated value, the beta hat you got in your undergraduate level, that value was summation xi yi divided by summation xi square. That was the value, summation xi yi divided by summation xi square. So here you are getting the similar kind of construct. Summation xi y is equivalent to x prime y. In the denominator, you got summation xi square. Now here we are applying the matrix algebra, so I cannot write x prime y by x prime x. So here we have to present the similar idea incorporating x prime x inverse. So beta hat OLS is given by x prime x inverse x prime y. Okay, so this is the series of value for beta hat OLS. Any question? So this is the set of normal equations. Remember that k number of normal equations, and this is the value. Okay. So for the numerical exercise, if you have notion about x, you will be able to find out x prime, then you will be able to find out x prime x inverse, and you will be able to calculate x prime y. Once you get these two values, multiply these two matrices and matrices to get the value of beta hat OLS. Okay, so if you understand the steps, the meaning, the logic, so I expect that you will be able to solve the numericals too. So do anyone have any question, or should I proceed towards the properties of beta hat OLS? Shubhangi, is it okay?
Yes, ma'am.
Orkodip? Naurin? Purnima? If anyone have any problem, please let me know. So if you understand the estimation part, next we are moving towards properties of OLS estimators. We bother about two properties: whether this estimated value is unbiased or not, that is whether expectation of beta hat OLS is equal to beta or not. Here you are understanding I'm talking about entire beta hat vector and beta vector. And we are also interested about variance of beta hat vector. Actually, in a classical linear regression model, we need to find the best estimators, best linear unbiased estimators, blue, best linear unbiased estimators, or the estimators following the blue property, so that we can move towards the Gauss-Markov theorem. Okay. So given the classical assumptions, if the estimators follow the minimum variance unbiasedness properties, in that case, we consider that Gauss-Markov theorem has been satisfied. So we need this construct. So we are moving towards properties of beta hat OLS. Looking at the structure of beta hat OLS, it is x prime x inverse x prime y. So we are understanding beta hat OLS is linear in Y, looking at the structure, okay? We are finding that beta hat OLS is linear in Y. So the first property we can mention, linear in Y. Since Y is a linear function of U, so will be beta hat, you know. So we are finding that beta hat is linear in Y. It is also linear in U. Okay. The second property, beta hat is unbiased estimator of beta if we can show that expectation of beta hat vector is equal to beta vector. If we can show expectation of beta hat vector is equal to beta vector, then we can claim beta hat is a series of unbiased estimators for beta. So let's start with beta hat OLS, which is x prime x inverse x prime y. So I expect everyone has pen and paper. So try to check the unbiasedness property on your own. Please write down this value. Beta hat OLS, beta hat is equal to x prime x inverse x prime y. Please write down this value. So everybody has this thing. What will be the first step? What I need to do in the first step? I need to show, you know, as I mentioned, I need to show expectation of beta hat is equal to beta. That I need to show. So what will be the first step? What I need to do in the first step? Anyone? Choyon?
हाँ मैम.
Yes, what I need to do? How I'll proceed? Anyone?
Ma'am, we could replace y
Yes.
with x into beta plus u.
Why I'll do so? Very good. But why I'll do so?
Ma'am, because we
Because
need we need to prove that that part is zero. So that is the way to go about it.
that's not a Nepali or for anyone. Actually, we have to bring you in our analysis. In a classical framework, all the assumptions center around you. So you is the focus of our analysis. So we have assumptions based on you. So somehow, whenever I'll try to find out anything, I have to bring you in the analysis because of assumptions, etc. So what Upali told us, that is absolutely right. We have to replace y by x beta plus u. Everybody, please do the thing. Okay, now if you do so, we will multiply. Here we are getting x prime x inverse, then x prime x beta. The first term will be like this, x prime x inverse, x prime x into beta. And what will be the second term? What will be the second term? Ujan,
X prime U.
only x prime u.
X prime X inverse X prime U.
Yes. This will be x prime, x inverse, x prime u. Now from the first term, what we are actually getting? Can we adjust everything and reduce the first term? What is the first term will be?
I didn't know that into B, beta. So it will be just beta.
It will be simply beta. X prime x inverse will be adjusted with x prime x, giving us the identity, and it will be beta only. If identity is multiplied with the beta vector, we will get back beta. So it is beta plus everybody. So in the next step, now expectation of beta, what it will be? Expectation. Yeah, why?
Ex- Expectation of U will be 0.
Expectation of beta will be 0.
Beta.
U. Expectation
Yeah.
of beta will be beta.
Expectation of beta will be beta. Since beta is a constant, expectation of beta will be beta plus x prime x inverse x prime expectation of u. This is equal to beta since expectation of u is equal to 0. Expectation of u vector is equal to 0 vector. So we are getting expectation of beta hat is equal to beta, and therefore beta hat OLS can be considered, or beta hat OLS is the series of unbiased estimators for k unknown values of beta. Is it okay to all of you? Clear? Titir?
Yes, ma'am.
Very good. Okay, so, we did this thing. Expectation of beta hat is equal to beta plus x prime x inverse x prime expectation of u. This is equal to beta as expectation of u is equal to 0 vector. Next step, so the first property is proved, or the second property. The first property is it is linear in y. The second property is it is unbiased. And the third requirement is minimum variance unbiased estimator. It should have the minimum variance. Now, before coming to the conclusion or the proof related to minimum variance, first we need to calculate the variance of beta hat. Now, if I need to calculate variance of beta hat, I have to calculate basically the variance covariance matrix of beta hat, where along the diagonal we will get the variances, and all of diagonal terms will give us the covariances. Okay, so we will be not able to find out only the variances. We can find out both the variance as well as the covariances. Okay, so please use your pen and paper. We will do the things step by step. So please write down where beta hat, that is the variance covariance matrix of beta hat, is equal to expectation of within bracket beta hat minus expectation of beta hat, then within another bracket beta hat minus expectation of beta hat transpose. So it is So this is expectation of this one. Now first try to understand the order, etc., so that you will understand this is a matrix rather than a vector. Now what is the order of beta hat? It is of order k by 1. So expectation of beta hat, this will also have the order k by 1. So this entire thing has order So this will have order. So this entire thing has order k by k. Are you agreeing with this matter? This product has order k by k?
Yes,
Or
ma'am.
it's a symmetric matrix. Okay, so it is a square symmetric matrix. Okay, so we started with a vector beta hat. However, we reached at a matrix of order k by k. So as rough work, when I tried to get residual, or better to say residual sum of squares, I considered E prime E. Here also I started with a vector of order n by 1. However, we need to reach at a scalar. So I multiplied the transpose with the original vector. So I got, something which is of order 1 cross 1. Here I need a matrix. Therefore, I am multiplying, from here also, if I need a matrix, in that case, what I'll do, I'll consider E transpose. This will be of order n by n. Okay, so it will be a matrix. So you need to be very, very careful about all these things. Whether you need a matrix or you need a scalar. If you need a matrix, your pre and post multiplication will be something. If you need a scalar, your multiplication rule will be different. Here, we need the variance covariance matrix. Therefore, I'm post multiplying the vector beta hat minus expectation of beta hat by its transpose. Okay, so remember these concepts very well because you have to do several things on your own. Now, if I look at our earlier steps, we got, beta hat is equal to beta plus x prime x inverse x prime u. Beta hat is equal to beta plus x prime x inverse x prime u. So beta hat minus beta is simply x prime x inverse x prime u. Beta hat minus beta is simply x prime x inverse x prime u. Now coming back to this is expectation beta hat minus beta as it is already proved. We proved that beta hat is an unbiased estimator of beta. Now, this is equivalent to is it okay to everyone? Beta hat minus beta I am replacing by x prime x inverse x prime u. Okay? Now, if I take transpose of the second term, please tell me what will be the value. What will be the value? Aditya? What will be the value if I take transpose?
Yes, ma'am. U prime x, x prime x inverse.
Slowly. This board is not that smooth, you know.
Yes,
You
ma'am.
trans
U prime x,
x,
x prime x inverse.
x prime x inverse. Very good. Okay, so you transpose x, and if you take transpose of x prime x inverse, you are not understanding which one was the first x and which one of the was the second x. So you will get x prime x inverse back. Okay, so we are at this position: x prime x inverse, x prime u prime x prime x inverse, etc. Now, in the next step, I'll operate expectation on the error terms. So I'm operating expectation on error term u prime. Now, what is expectation of u transpose?
0.
0? Is it 0?
Sigma squared
Sigma square in. Okay. Expectation of u prime, that is sigma square in. Because here also we cannot separate autocorrelation from the idea of homoscedasticity. Basically, we are talking about the variance covariance matrix of the error term. So here there is the joint assumptions of homoscedasticity and non-autocorrelation. So the expectation of u prime is nothing but sigma square in. So sigma square is a constant. So we can just a minute. Is it okay? So if this is okay with you, in that case, 1x prime x can be adjusted with x prime x inverse. So I can adjust this term with any one of these two inverse. Okay. So finally, what I'll get, that is given by sigma square x prime x inverse. So this is the value of variance of beta hat. The variance covariance matrix of beta hat is given by sigma square x prime x inverse. Any question? Any question, any confusion? Now in a two variable case, as again a rough work, in a two variable case, what was the value of variance of beta hat? It was sigma square by xi square. This was the value of variance of beta hat, sigma square divided by summation xi square. And here, in terms of the matrices, we are getting the similar concept. You know, sigma square x prime x inverse. Here we are getting the entire variance covariance matrix of the beta hat, you know. So there is term along the diagonal, there is terms along the off diagonal. So off diagonal terms will be the covariances between the regression coefficients, whereas the diagonal terms will be the variances. You know, however, I have written the structure of variance of beta hat in the two variable analysis so that you can relate the things. Whatever you learned earlier, we are extending these things only, okay, using the matrix algebra or using all k variables in our analysis. So any question, any query regarding the calculation of variance of beta hat? Okay, so this beta hat, now what we need to do, we need to consider any other beta hat, you know, any other estimator. This is the OLS estimator, x prime x inverse x prime y, that is the OLS estimator. So we need to take any other estimator and we need to consider the variance of that other estimator, and then I need to compare the variance of that estimator with these particular variants, and I need to come to the conclusion that this variance is lesser than that of the earlier one. However, the entire analysis in terms of matrix algebra is a bit complicated. So for this year, I am not considering that exercises in the class. However, whatever you learned earlier in case of two variables, please practice that thing. Okay, I hope you went through the books like Ulrich or Madala or Johnston and Donato, the books which are the basic texts actually at undergraduate level. So in any book, you will get the derivation, etc. in a two variable chapter where they are considering an alternative estimator, alternative unbiased estimator, and linear and unbiased estimator, and calculating the variance, then comparing it, etc., and coming to the conclusion that OLS is giving us the minimum variance. So you practice that thing. If anyone has any difficulty, then let me know. I'll try to give answer to that particular student. And if any one of you are interested about the calculation of the entire thing in terms of the matrix algebra, then also let me know. I'll send you a note on that. But in the class, I'm not discussing it. However, in exam, if I give question on compare the variances of two estimators, that will be based on two variable analysis. Okay, so what you did at your undergraduate level. So here I am writing that beta hat is the minimum variance unbiased estimator in VUV, leaving the exercise just calculating the variance covariance matrix, but not calculating variance covariance matrix of any other linear unbiased estimator here and comparing them, mentioning that beta hat is minimum variance unbiased estimator, that is in class of all linear unbiased estimators of beta hat, the OLS estimator has the minimum variance. Okay, and first I talked about unbiasedness, then I am talking about the minimum variance property. Combining this, we can claim that beta hat OLS is the based linear unbiased estimator. Okay, beta hat OLS is the based linear unbiased estimator. So, please complete your homework, everyone. Please check your previous notes, or please check any book appendix of the two variable chapter. You will get the calculation. Okay, that if you consider any other linear unbiased estimator and calculate the variance, that variance will be higher than that of OLS. Okay, so if you can prove it or understand the proof of with the two variable case, then simply I can extend it and I can argue for for k variable case, or if I extend the model for k number of unknown parameters, then also this property will be satisfied. So are you understanding what you need to do in your home? Shraya, Twinkle, Shreya Noshkar, Rudro, Purnima, are you understanding what you need to do? Or
Yes, ma'am.
so please check everything properly. Okay, so in the estimation, we need to discuss about one other estimator. The estimation of the parameters is complete. However, we need to derive the estimated value of the population variance too. That is, we need to find out the estimated value for sigma square. Under most of the circumstances, the sigma square is unknown. Sigma square is the population variance. And under most of the circumstances, this is unknown to us. So before moving towards hypothesis testing, we need to learn how we can derive an unbiased estimator for sigma square. So we need to derive an unbiased estimator for population variance sigma square. So just before coming to these, estimation, etc., in our rough work, we presented the variance covariance matrix of the U, okay, expectation of U prime U, and we got this is sigma square IN. So what I am telling, under most of the circumstances, this sigma square is unknown, and therefore the entire variance covariance matrix remains unknown to us. Hence, we need a suitable estimator for this sigma square. So anyone can remember what was the estimator for sigma square in a two variable case?
RSS by n minus 2.
RSS by n minus 2. Very good, Rudra. Rest of the students, can you remember this? Shubhangi, Naureen, can you remember these things? RSS by degrees of freedom we found.
Yes, ma'am.
Okay, so we need to find out the same measure, we need to find out the same measure or similar kind of measure here in context of k variables, okay? So now we are moving towards calculation of unbiased estimator of error variance. Okay. Now, the unbiased estimator of variance of ui, which is equal to sigma u squared, that we need to find out. Now, to derive the unbiased estimator of the sigma u squared, we may start from variance of ei. Why? Because in context of estimation, the entire estimation process, I mentioned that UI is not realized, UI is not observable, And therefore, we bring a proxy for Ui, and we considered Ei as that proxy, the residual as that proxy. So when we are finding a problem that we have no knowledge about sigma u square, which is the variance of Ui, why not we start with variance of Ei and check whether variance of Ei is an unbiased estimator for variance of Ui. Now, what is variance of EI? Variance of EI, I'm using the simple formula because EI is not random. So it is yi minus yi hat. So it is based on calculated values, So we can use this basic definition 1 upon n summation ei minus e bar whole square. Now, what about e bar? By the normal equation, we get summation ei is equal to 0. So if you consider your two variable case, when we are taking derivative with respect to alpha, beta, etc., we get the normal equations as summation ei is equal to 0, which is the first normal equation. So first normal equation tells us summation ei is equal to 0. So summation ei by n or e bar will be also equal to 0. So variance of ei is equal to 1 upon n summation ei square, which is equivalent to RSS by n. So we may try variance of ei, which is RSS by n, as an unbiased estimator of sigma u square or not. So we may start with these RSS by n, this concept. So once again, I'm coming to the concept of RSS. RSS is equal to E transpose E. Now E is yi minus yi hat, or E is equivalent to y minus x beta hat. Now beta hat is equal to x prime x inverse x prime y. So E can be presented as y minus x, x prime x inverse x prime y. Okay. Now y, this y can also be presented as x beta plus u. And this y is also x beta plus u. So if I replace both the y values by x beta plus u, the first y is x beta plus u. Now here x prime x into x prime x inverse x prime x beta plus u. Okay. So if I write the term in that way, please write the thing in your copy. X prime x, x prime x inverse, x prime x beta. So you will find that x prime x will be adjusted with this x prime x inverse, and you will get x into beta only. And there is another term, u. So if you multiply u with this, you are getting x, x prime x inverse, x prime u. So are you getting x beta when you are multiplying x, x prime x inverse x prime with x beta? Are you getting back x beta only? Are you doing the things? Getting the values or not? This is econometrics class, you need to be very active and write the things properly and do the things first. Orithro, are you getting it? Upali got it?
Yes, ma'am.
So if you get it, please let me know. If anyone have any problem, that also please tell me. The classes should be interactive, otherwise, it will be very, very difficult to understand whether you are understanding the things or not. So, as I replace both the y by x beta plus u, we are getting this kind of equation. Okay. And as I get this first x beta will be cancelled by this x beta. So I have u plus x prime x inverse x prime u. So if I take u common, it is I minus x prime x inverse x prime. Now I of order n because u is of order n by 1. Now this I minus x prime x inverse x prime is an idempotent matrix. I minus x prime x prime x inverse x prime. This is an idempotent matrix. I sent you a note on idempotent, the matrix algebra, and I hope all of you went through this and you have idea about the idempotent matrix. Okay. So E transpose E can be presented simply by mu, idempotent matrix multiplied with u vector. So mu. Okay. Now, if M is an idempotent matrix, that implies M transpose is equal to M square is equal to M cube is equal to M, etc. This is the property of idempotent matrix. So I can write E transpose E as U transpose M transpose MU. E is MU, E is equivalent to MU, and then I am writing the RSS or E transpose E transpose E. So E transpose is U transpose M transpose, and that will be multiplied with MU because E is equivalent to MU. Now, U prime, M prime, MU can be simply presented by U prime MU because M prime M is equal to M. Square is equal to that value for the idempotent matrix. So, I'll calculate expectation of E transpose E, which is equivalent to expectation of U prime MU. Now, to understand how I'll calculate expectation, etc., it's better to consider a 2 by 2 matrix. So the things will be understandable. So I'm considering M to be equal to 2. So expectation of U transpose MU can be presented as expectation U, if I consider originally a column vector, transpose will be the row vector. Then the idempotent matrix M11, M12, M12, M22 multiplied with the original U vector U1, U2. So this will result in M11 U1 square, M22 U2 square plus 2 M12 U1 U2. I'll take expectation or operate expectation on each of the error terms. So it is M11 expectation of U1 square, M22 expectation of U2 square, 2 M12 expectation of U1 U2. Now, by the assumption of homoscedasticity, expectation of U1 square is equal to expectation of U2 square is equal to sigma U square. And by the assumption of non-autocorrelation, expectation of U1, U2 is equal to 0. So this entire thing reduces to M11 plus M22 into sigma U square. Now, what is M11 plus M22? This is the sum of diagonal elements of a squared matrix. The sum of diagonal elements of a squared matrix is called the trace of that matrix. Trace of the matrix is nothing but sum of the diagonal elements in a squared symmetric matrix. So basically, therefore, expectation of U prime mu is trace of the idempotent matrix multiplied with sigma U square. This condition will hold for U of order n by 1, 2. Here I talked about 2 dimensions. However, if I incorporate all n dimensions, then also this property will hold. That is,
Ma'am,
yes.
ma'am, in the matrix M11, M12, and then it should be M21, no?
Earlier also, I mentioned in a symmetric matrix, since M21 is equal to M12, therefore I'm replacing it by M12.
Oh, okay, ma'am. Okay, ma'am.
Okay. So what I am telling, this condition, that is expectation of U prime mu is equal to trace m into the constant variance, this condition will hold for the error vector of order n by 1. So,
Ma'am, could you explain once more what is the trace of the matrix?
please go through the note on matrix algebra. It is the sum of the diagonal elements of a squared symmetric matrix.
Okay.
M11 plus M2 to here. I sent you the entire material 1 week back. Okay? You
Yes,
need
ma'am.
to take all these things carefully. Okay? So, so trace M, trace M for this particular M, this particular M is In minus x prime x inverse x prime. Okay. This is this M, In minus x prime x inverse x prime. Okay. So there are several properties of trace. Trace A minus B is equal to trace A minus trace B. Trace A plus minus B is equal to trace A plus minus trace B. So let's look at the note on algebra. So this is the note on idempotent matrix. This is the note on trace. Okay, for a square matrix, trace is summation aii, which is called trace or spar of a matrix. Then there is a numerical example how we are calculating the trace. And then there are properties. Trace A plus minus B is equal to trace A plus minus trace B. Trace ABC, CA. Please mute your microphone. It's disturbing. Trace ABC is equal to trace BCA is equal to trace CAB. Okay, so these are the properties of trace. Shubhangi, what's the problem? So these things are there. Okay, so already these things are there. Properties of trace, etc. Meaning of trace. So here trace in minus trace x prime x inverse. We are getting trace in, then trace x prime x inverse. This is also, actually what I am doing, trace of this is basically, trace say a, b, c. The first term say x is equivalent to a. X prime x inverse is say b. X prime is say c. So trace ABC is equal to trace BCA is equal to trace CAB. So I'm using that formula CAB, C x prime x prime x inverse. So I'm using the property of that, using that property of trace. Trace of ABC is equal to trace CAB. Now, if you do so, you are multiplying x prime x with x prime x inverse. So you are getting identity matrix, and here identity matrix of order k. So trace M is basically trace IN minus trace IK. So here you have identity matrix where you have n number of 1 along the diagonal. So if you consider 1 plus 1 plus 1 n times, you are getting the value n. And here trace IK, that means you have one identity matrix where you have k number of 1 in the diagonal. So you are getting the value k number of 1s. So trace M finally reduces to the value n minus k. So I started with expectation of E prime E, which is equivalent to expectation of U prime MU, okay, that reduces to, in terms of trace M into sigma U square. Trace M is nothing but n minus k. So finally, expectation of E prime E is equal to n minus k into sigma U square. So sigma U square is RSS by, it is expectation of RSS by n minus k. So expectation of E prime E is equal to expectation of U prime mu is equal to sigma U square into n minus k simply. So we can write expectation of E prime E by n minus k. This is equal to sigma U square, or E prime E by n minus k appears to be an unbiased estimator for sigma U square. So SU square is equal to RSS by n minus k is the unbiased estimator of sigma U square. So in this way, in a two variable case, you mentioned RSS by n minus 2. Actually, the estimator is RSS by degrees of freedom. In a k variable case, we are getting RSS by n minus k, that is appearing as an unbiased estimator. Okay. So similar kind of thing. Now there is a note, since trace M is equal to n minus k and the characteristic roots of M are either 1 or 0. Hence exactly n minus k columns of M are linearly independent and the remaining k are not. So the system has n minus k degrees of freedom. Some students have questions on degrees of freedom, and I told you I'll clarify the notion of degrees of freedom. So leaving this note, tell me whether you are understanding, SU square is equal to RSS by n minus k, that is appearing as the estimator of sigma square. So first tell me whether you are understanding this part or not. However, you should have grip on matrix algebra to understand all these issues. Okay, there is the issue related to idempotent matrix. There are issues related to trace of the matrix. We are using properties of trace, So using all these things, we are reaching here. So you need to understand all the steps, all the ideas clearly. Any question up to this?
Ma'am, I had a question.
Yes, yeah.
Ma'am, we are considering in minus x into x prime x inverse x prime to be m. Are we in that equation? Are we considering that part to be an idempotent matrix, or are we deriving it?
Upali, this is your homework to check, consider this matrix, in minus x, x prime, x inverse, x prime, okay? Multiply this matrix with the similar matrix, transpose of this matrix, I minus x, x prime, x inverse, x prime transpose. And please check whether you are getting back these or not. Because if it is an idempotent matrix, M transpose is equal to M, or the property we are considering, M is equal to M square. Okay. So this property will be satisfied here. So if you look at the definition of the idempotent matrix, there was some example and I mentioned, A is equal to A square is equal to A cube. If this happens, it will be an idempotent matrix. So for this matrix, please try whether in minus x, x prime, x inverse, x prime, if it is multiplied with its transpose, you are getting back this one or not. Okay? If you get back, in that case, it is an idempotent matrix. So these work you need to do.
Okay, ma'am. Thank you.
Okay. Next. Any other question? So if you do not have any question, so my estimation part is more or less complete. So we have completed the assumption in the last class, and now the estimation part is complete. And next day, we will move for different types of hypothesis testing in our k-variable analysis. Okay. So, our syllabus for internal assessment will be up to hypothesis testing for k-variable analysis. Okay, so all the assumptions will be there, or the estimation, the entire thing discussed today, that part will be there, and hypothesis testing will be also there. So these three sections of k-variable analysis will be the syllabus for your internal assessment exam. Okay, this is the first thing. Second thing is, as I mentioned, your practical sessions will start from next week. So it will take some time to start the internal assessment on Stata practical. Maybe Pravesh will be able to do that. However, I'll be not able to do it before last week of February. Okay. So at this moment, you will have exams for micro, macro, mathematical economics, and econometrics for 4 theory papers. For the practical, I'll discuss the matter with Pravesh, and then I'll send you the date, etc. For Stata, at this moment, you will have no internal exam. So if you have no other question, in that case, I can clarify the notion of degrees of freedom once. Now, those who have question on degrees of freedom, please tell me what is the question. Or in general, you want to know about the idea of degrees of freedom. Or the idea of degrees of freedom is now clear to all of you.
Ma'am, my question is why ESS have 1 degree of freedom?
ESS has
1 degrees of freedom.
ESS does not have 1 degree of freedom.
Well,
Are
for
you?
a two variable regression model.
Yeah. Because you have one explanatory variable only. Okay. So if you look at the ANOVA structure, we will later discuss on these two. Okay. And the regression model is so there is only one explanatory variable in your analysis. This is the structure, you know. And for this, you know that degrees of, what is the degrees of freedom for RSS?
N-2.
N-2. In a k variable analysis, it will be N-k. Okay. And what is the degrees of freedom for TSS? Actually, it will be the summation of degrees of freedom of these two things, you know, degrees of freedom of ESS plus degrees of freedom of RSS will give you the degrees of freedom for TSS. In a k variable analysis, you have k minus 1 number of explanatory variables. Okay, so k minus 1 plus n minus k will give you n minus 1. Here you have one explanatory variable and the other one is the alpha is nothing but the intercept of the model. Okay, so here your degrees of freedom will be 1. For ESS, the degrees of freedom will be given by the number of explanatory variable you have in the analysis. Okay, and if you adjust, it is n-1 for the 2 variable case. Okay, since you have one explanatory variable, so you have 1 degree of freedom. Okay,
Thank you, ma'am.
and here for RSS, you are getting n-2 because you have n observations in your hand. Using n observations, you need to estimate 2 unknown parameters, alpha and beta. So the degrees of freedom you have, that is n-2. Because 2, you are losing one to calculate beta and another to calculate alpha. The similar thing in case of k variable analysis is becoming n-k because we are losing k degree of freedom to estimate all the parameters starting from beta 1 to beta k. So we have n-k degrees of freedom. And using these degrees of freedom, we can estimate some other parameters too. Today, I have derived a square, which is an estimator of sigma square using the same notation of E prime E. So I'm using 1 degree of freedom out of n-k to estimate that parameter. Okay, so we need some degrees of freedom in our RSS so that apart from k number of parameters, we can estimate some other unknown elements in our analysis. So any other question, anything?